Hello everybody, my name is Shiva Tejesh. In this video, we will be discussing about circular convolution of two discrete Fourier transforms. Before we go into the specifics, let us talk about convolution in general. Convolution is a mathematical way to combine two signals to form a third signal, one of which is the input signal and the other the impulse response of the system. It is one of the most important techniques in digital signal processing. There are two types of convolutions, linear convolution and circular convolution. Let us talk about linear convolution briefly. Linear convolution is a mathematical operation done to calculate the output of any linear time invariant system when its input and the impulse response are given. It is applicable for both continuous and discrete time signals. We can represent linear convolution by the following equation. Y of n is equal to x of n star h of n, where y of n is the output, also known as the convolution sum. In linear convolution, both the sequences may not have the same number of samples. The number of samples in the output sequence is equal to m plus n minus 1, where m is the number of samples in x of n and n is the number of samples in h of n. Now, let us discuss in detail about circular convolution. First, we will look at the features of circular convolution, after which we will go into the process. Circular convolution is essentially the same process as linear convolution. Just like linear convolution, it involves the operation of folding a sequence, that is time reversal, shifting, multiplication of the sequences, and then summing the product. However, in circular convolution, the signals are all periodic. Thus, the shifting can be thought of as actually being rotation. Since the values keep repeating because of the periodicity, hence it is known as circular convolution. Circular convolution is applicable for both continuous and discrete time signals. In circular convolution, both the sequences, input and impulse response, must be of equal sizes. That is, they must have the same number of samples. In some cases, if both the sequences have different number of samples, then the sequence with the lesser number of samples is appended with zeros at its end to make the two sequences equal. This is called zero padding. The output of a circular convolution is always periodic, and its period is specified by the period of one of its inputs. Now let's go straight into the process of circular convolution. Let us take two finite duration sequences, x1 of n and x2 of n, of length n, with their endpoint DFT is given by the equations 1 and 2. The product of two DFTs is a DFT. Let us take x3 of k to be a DFT, which is the product of x1 of k and x2 of k. The inverse discrete Fourier transform of x3 of k is given by the equation 4. Substituting the equations 1 and 2 in the equation 4, we get equation 5, which is x3 of m is equal to 1 by n summation of n is equal to 0 to n minus 1, x1 of n into summation of L is equal to 0 to n minus 1, x2 of L into the summation of k equal to 0 to n minus 1, e to the power of j 2 pi k whole m minus n minus L by n. Let e to the power of j 2 pi m minus n minus L by capital N is equal to a. Then the summation of k is equal to 0 to n minus 1, a to the power of k is equal to n if a is equal to 1, or 1 minus a to the power of n by 1 minus a if a not equal to 1. If we substitute the value of a in equation 5, we get the equation 7. The expression in equation 7 has the form of a convolution sum. However, it is not the ordinary linear convolution which relates the output sequence y of n of a linear system to the input sequence x of n and the impulse response h of n. Instead, the convolution sum in equation 7 involves the index m minus n of n and is called circular convolution. Thus, we conclude that the multiplication of the discrete Fourier transforms of two sequences is equal to the circular convolution of the two sequences in the time domain. Now, let us look at the sample problem in order to understand the concept a little better. We have two sequences x1 of n which is equal to 2, 1, 2, 1 and x2 of n which is equal to 1, 2, 3, 4. Each sequence consists of 4 non-zero points. For the purposes of illustrating the operations involved in circular convolution, it is desirable to graph each sequence as points on a circle. Thus, the sequences x1 of n and x2 of n are graphed as illustrated in the figure A. We note that the sequences are graphed in a counterclockwise direction on a circle. This establishes the reference direction in rotating one of the sequences relative to the other. Now, x3 of m is obtained by circularly convolving x1 of n with x2 of n as specified by the equation 7. Beginning with m is equal to 0, we have x3 of 0 is equal to 1 by n summation of n is equal to 0 to 3 x1 of n into x2 of minus n. x2 of minus n is simply the sequence of x2 of n folded and graphed on a circle as illustrated in figure B. In other words, the folded sequence is simply x2 of n graphed in a clockwise direction. The product sequence is obtained by multiplying x1 of n with x2 of minus n, point by point. This sequence is also illustrated in figure B. Finally, we sum the values of the product in the sequence to obtain x3 of 0, which is equal to 14. For m is equal to 1, we do the same process except m is taken as 1. It is easily verified that x2 of 1 minus n is simply the sequence x2 of minus n rotated counterclockwise by 1 unit in time as illustrated in the figure C. This rotated sequence multiplies x1 of n to yield the product sequence, also illustrated in figure C. Finally, we sum the values in the product sequence to obtain x3 of 1, which is equal to 16. Now, repeating the same process for m is equal to 2 and m is equal to 3, we obtain x3 of 2 is equal to 14 and x3 of 3 is equal to 16. Now, combining all the values we got for x3 of m, we obtain the entire sequence. x3 of m is equal to 14, 16, 14, 16. From this example, we observe that the circular convolution involves basically the same 4 steps as ordinary linear convolution. That is 1. Folding, time reversing one sequence. 2. Shifting the folded sequence. 3. Multiplying the two sequences to obtain a product sequence. And finally 4. Summing the values of the product sequence. The basic difference between the two types of convolution is that in circular convolution, the folding and shifting, that is rotating operations, are performed in a circular fashion by computing the index of one of the sequences modulo n. In linear convolution, there is no modulo n operation. Thank you.